So the next talk is entitled Failing to Hash into Supersingular Isogeny Graphs. It's going to take Morse advice not to read all the names. Ross, the floor is yours. I don't think we can hear you. The first speaker is remote.
Yeah. I think it's him.
We cannot hear you, Ross. I think it might be a problem on your end. We can see you, but we cannot hear you.
How very CFAIL. Okay, now let me find my slides again. Okay, sorry about this. Thank you for the introduction, and thank you to the organizers for allowing me to participate virtually, however many hiccups there might be. And yeah, so today I'm going to talk about our attempts to hash into the supersingular isogeny graph. And this is joint work with Sabrina and Kate, who are there in person, and many others. And I won't read out all their names because it might take a while. So what is this about? I'm going to first give an overview of what these words mean, what this problem is, and then describe some of our many attempts to solve this. Okay. So this problem takes place in the setting of isogeny-based cryptography, which is a relatively new area of asymmetric crypto that's gained a lot of traction in the past few years. And it lives within the realm of elliptic curve crypto, which I expect you're all somewhat familiar with. But now we're rather than working with the points on elliptic curves, we're looking at the elliptic curves as the objects themselves and considering maps between them. And the reason this is of interest to cryptographers is this problem here, which is called the supersingular isogeny problem. And this is the problem that says, okay, if I give you two curves defined over some finite field, can you find some map between them? So these maps we call isogenies, and they're group homomorphisms. And we believe this problem is hard, both classically and quantumly, right? Which is why it's gained a lot of traction recently with the need to transition to post-quantum forms of asymmetric crypto. Okay, and then another problem that appears in this realm is the endomorphism ring computation problem. And this is the problem of, if I give you a supersingular curve defined over a finite field, can you describe all the isogenies from that curve to itself? Okay, and this is a problem that looks at first maybe it's not so obvious that this is equivalent to this, but this is in fact equivalent to the first problem, assuming the generalized Riemann hypothesis, in the sense that there is a polynomial time reduction from one to the other. Okay, and then in this setting, we can then build some asymmetric crypto. So we said that this supersingular isogeny problem is hard, but actually going in the other direction is easy, with some technical details, in that if I give you a starting curve and the description of some isogeny, then computing the codomain can be done efficiently, assuming the degree of this map is smooth. So you can have a sort of secret key, public key setup in this form, where your secret key is some isogeny to a curve, and then your public key is that curve. Okay, and then a question you can ask in classical discrete log crypto, for example, is there a way to generate public keys without first generating a secret key and then computing the corresponding public key? So this is something that's studied in the form of elliptic curve cryptography, I guess. And so it's natural to ask the question in this setting too. And so concretely, what we want to do is if we define this set, and these are supersingular elliptic curves over a finite field up to isomorphism. Then this is a finite set. It has OP, its size is OP, and then the problem we want to solve is to sample from this set in such a way that we don't reveal anything about the endomorphism ring of our final curve, or equivalently, as we said, a path to E from some known starting curve. And then some variants of this problem we could also ask is once we've got an example of one curve, we call it a hard curve. This curve with unknown endomorphism ring. And so once we have one, the question is, can we construct an algorithm that samples many from this set, SSP? Okay, and then a slight variant of that is, could we then define a hash function to that set? So one that has some of the properties you see in a standard cryptographic hash function. Okay, and so some applications that, well, why are we interested in this problem? Several protocols have been made in the sphere of isogeny-based crypto, and within those constructions, it's been observed that there are attacks you can perform when you use within your protocol some starting curve with known endomorphism ring. So some examples here are hash functions based on isogenies. You can show that you can find collisions on this hash function if you start from a curve with known endomorphism ring, and that's closely related to finding an attack on some commitment schemes based on isogenies. And then there are some more advanced protocols such as verified relay functions and delay encryption that you can also show attacks against if you use curves with known endomorphism ring. And then a topic that's quite newsworthy at the moment is this key exchange protocol called SIDH and its concrete instantiation called Psych. And so in the past few years, there have been these types of attacks called torsion point attacks. And these, combined with some information on certain isogenies, together with knowledge of the endomorphism ring of some curve, you can demonstrate attacks on this key exchange or unbalanced variants of this key exchange. And so one application for demonstrating a hard curve would be to use this as a starting point, so a public parameter in this key exchange, and that could avoid these attacks. At least this was the case until about 2 weeks ago, when Weitkämper and Thomas de Croo found a polynomial time attack on SIDH. And this uses heavily the knowledge of the starting, the endomorphism ring of the starting curve. And so this problem kind of had its brief moment in the limelight. It was, thought this would be one of the only ways to rescue SIDH. But a week later, there was another attack by Luciano Mono and Chloe Martindale that have proposed a variant of this where knowledge of that endomorphism ring is not actually leveraged. And there's even been papers even more recently sort of developing these ideas. So I don't want to say anything too concrete on this because it will probably be outdated within 5 minutes or so. We know that supersingular curves exist, and we already have examples of them. So why do the approaches we use to generate them, why are they insecure or not fit for our purpose? And so one properties that supersingular curves have is if you consider all of them up to isomorphism and their isogenies, then they form expander graphs, which look a bit like this pretty picture. And a property of expander graphs is that if you take a random walk in this graph, then you quickly reach a uniform distribution on all the nodes. And so one idea you could use to sample a random elliptic curve is to start from some point in this graph, take a random walk. That walk only doesn't have to be too long because this graph is expanded, and then you could use the end curve as your output. Okay, but this is clearly generating a path from your starting curve to your output curve, and in any instantiation, your starting curve is going to be one with known endomorphism ring. So this is clearly generating leakage of a path to your final curve, which is what we want to avoid. So an approach that's a bit less obviously unsuitable is this algorithm of Broca's. And this uses properties of elliptic curves defined over a characteristic zero field, so defined over Q typically. And one property of supersingular curves is that they have very large endomorphism rings compared to elliptic curves in general. And so the idea here is if you start with an elliptic curve with complex multiplication, which just means you have a larger than typical endomorphism ring. Okay, and then you can reduce this mod sum prime P. And then for about half of those primes for which you can define this reduction, you'll end up with a supersingular curve. So this looks like, so this is the approach that Broca's algorithm takes to obtain supersingular curves defined over a finite field, is that if I give you the prime characteristic of your field, then you can compute another prime Q, which has some technical conditions on it, but these are easily satisfied. Then you can compute the Hilbert class polynomial of this field Q, and the roots of this polynomial will give you invariance of supersingular elliptic curves. Okay, but the problem with this is that this Hilbert class polynomial is only feasible to compute for a very small Q. And essentially, when you have small Q, this gives you curves with small endomorphisms, and some work by Dan Bonnet and Jonathan Love have shown that computing isogenies between curves with small endomorphisms can be done efficiently. Okay, so these are the two methods we currently have to sample supersingular curves, and this is why they fail. So now we're going to talk about some of the approaches we took and why they also do not work. And so, any approach we're going to use is going to have to leverage some properties of supersingular elliptic curves. And one of them is that if you look at their rational set of points, then this is a set of order p plus 1. Okay, so one idea we had is if you consider a polynomial that has this property where given some curve parameter lambda, you can look at the difference from p plus 1 to the set of rational points on this curve. And then the supersingular curves are precisely the roots of this polynomial. Okay, now, because lambda varies over some field of order p, then this is a polynomial of exponential degree, so we can't actually write it down. But written in this form, what we can do is evaluate this polynomial on any input. Okay, and so if we want to find a root of a polynomial that we can evaluate, then this is a similar method, a similar setting in which you could do some sort of Newton iteration to find a root. And so this is our strategy, is to define this iteration here, where we obtain our next lambda from the previous lambda evaluated at h divided by h prime. So this is exactly the sort of setting you're in when you do Newton-Raphson iteration. Okay, and then the roots of h precisely correspond to the fixed points of this iteration. Okay, and then the hope would be that we could pick some seed as our input and then compute this iteration until we reach a fixed point. And we said fixed points correspond to roots. We may end up in a cycle in which we can resample a seed and try again. Okay, and HP we can evaluate efficiently, but what we would need in order for this to be an effective method is for the number of steps we have to take to be small. Even if each computation is efficient, but we have to do exponentially many of them, then this is not going to be feasible. So the question we really want to answer is, after how many iterations of this map do we expect to reach a fixed point? Okay, and this is an analysis we performed. So we considered random maps on a finite set X, and with a prescribed number of fixed points. And we asked the question, if we perform k iterations of this map, how many of the points in X do we expect to reach a fixed point? And we did this analysis, and our conclusion was that the proportion of seeds that will reach a fixed point is this quantity asymptotically. So k plus 1 times the number of fixed points divided by the size of X. Okay, and this is unfortunate because in our case, we, in order to have a non-negligible probability here, we need k to be of order root p, which is x managed 1p. So this is unfortunately not a feasible method. And then just to add, this was for analysis was for a random map, but in what we find is that this our concrete map also behaves in this manner. Okay, and so this approach is doomed to fail, and I think at this point I'm hopefully passing over to Kate. Kate, are you there?
Presentation mode. Is the yeah, this one? Okay, great. So now we have all catching up to do. Okay, great. So so if I looked at the clock correctly, we have about 15 minutes to do 4 more approaches. So we'll probably fail to do that. So so this approach is based on the modular polynomial. The this polynomial in 2 variables, x and y, which vanishes exactly when x and y as J invariants are connected by a cyclic n isogeny. And we're going to specialize this polynomial so that y is the Frobenius conjugate of x, and consider it mod over fp. And that means that it'll have roots, which are J invariants that have a cyclic n isogeny to their own Frobenius conjugates. Okay, so it's still too big to deal with, and the idea here is to consider 2 such polynomials and take their GCD. So if we've got this, this polynomial f n m p, the idea for finding a hard supersingular curve would be to cleverly choose n and m, and then compute roots over fp squared, since we know all the supersingular J invariants will lie over fp squared, and then test if they're supersingular. So looking at this, you wouldn't necessarily have hope, but there are a few reasons why this might work. First, there are heuristic reasons why this polynomial, this GCD in particular, should have predominantly supersingular roots, whereas the individual polynomials wouldn't. One way to see that is to think about the endomorphism ring, which is bigger in that case. And when you have both an N and an M isogeny to your conjugate and the Frobenius, you have a lot of endomorphisms of known degree, NP, MP, and M. And so you need a bigger endomorphism ring for that to happen. So that's one heuristic reason. We can also do a heuristic to count the number of roots, and what's important is that over fp squared, those are the roots we would be looking for, there's around square root nm heuristically. So we can actually give an algorithm which is polytime in nm and log p, even though the polynomials themselves would appear to have exponents as big as p, using Weil descent to get rid of those exponents. But the fundamental problem with this approach is that we would actually have to choose at least one of n and m to be large. Because if you have both an n isogeny and an m isogeny to your conjugate, then you can go n and back along m and get an nm degree endomorphism, and that's a small endomorphism, and that's a weakness. And so we have to avoid those, and now this algorithm is not fast enough. Okay, so some of the ideas might be, could we replace that algorithm with something better? Maybe take three-way GCDs to make those polynomials smaller, and so on. All right, oh, I forgot that I had a tiny bit of data here. We had a lot of fun creating some data. So this shows, this graph is on the x-axis square root nm, and on the y-axis is the number of FP squared roots. So this kind of demonstrates the first heuristic about the degree is at least believable. And this is counting the proportion, the y-axis here is the ratio of supersingular roots over all the roots. And when they're coprime and not coprime, the n and m's. And the red line is the average, so it's in the 90s. So we really are seeing supersingular roots. Okay. Green to advance.
Okay, so I'll present the next two approaches. The first one is called reverse Schoof. So let me first remind you what Schoof's algorithm is. That's an algorithm for computing the number of points of a given elliptic curve over some finite field. And what does it mean that we want to reverse this algorithm? We want to go the other way now. We are given some number n and a finite field, and we want to find an elliptic curve that has precisely this number of points. Why is this helpful for finding a supersingular elliptic curves? That's because we can characterize supersingularity by the number of points on the curve. For example, if we just look at a prime field Fp, then the curve is supersingular if and only if it has exactly p plus 1 points. So the idea would be to find a curve with p plus 1 points. In general, this is constructively not so easy, but one can use a prime of a very special form, and such primes are actually used in supersingular isogeny protocols. For example, here I've written down a prime that is the product of many small primes, Li minus 1. In that case, if you now compute p plus 1, you see that the number of points of the elliptic curve is just the product of small primes. And if we go to a field extension of degree 2, one can check that now we have those small primes to the power 2 in our product. And this means that actually all the Li torsion is rational, or is defined over Fp squared. So what is torsion? A torsion element is just an element, so an L torsion element would be an element that if we multiply it by L, we get 0 again. So these are the points of order Li. Okay, so how can we use this to construct an elliptic curve? So we look again at a prime of this form as before, and say we have an elliptic curve that is defined by some parameter A. For example, a coefficient of, like the Montgomery coefficient or J invariant or so. And what we can do is we can write down the L division polynomials. Division polynomials are the polynomials that have as roots the x-coordinates of torsion points. So what we know, since, as I said before, the L torsion is rational, this means that these division polynomials that depend on the curve parameter A have rational roots. So with rational, I always mean defined in Fp squared. And like that, we can define a system of polynomial equations where we have these division polynomials that are supposed to be 0, and then we have one further condition that is used to guarantee that those x-coordinates are actually in the finite field Fp squared. And what is nice, so yeah, so solutions to this, if we can solve this polynomial system for A, then we will actually find, then A will be a parameter defining a supersingular elliptic curve. And what's nice about the system is that the degrees of the polynomials involved are not very large, and it also doesn't contain so many mixed terms. So yeah, maybe if it's not clear from here, we have, this is a polynomial system with many variables. So the xli's are all variables, but we don't have that many mixed terms. So in theory, it should be easier to solve this polynomial system than a generic system. And unfortunately, we still don't know how to solve it efficiently. But compared to the other methods, it's at least something that one can write down and know how the solution would look like. Okay, so let's reverse proof. So now we are going to look at a bit more geometric approach, and we need some algebraic geometry, but I will try to not go into too many details about that. Here we are looking at the generalization of elliptic curves, those so-called abelian surfaces. So if you think of an elliptic curve, that's a one-dimensional object. So in some sense, it's just a line with maybe a funny shape somehow. And now if we want to generalize this, we get something two-dimensional. So that's like a plane, but also again with some weird shape. So this is how you can imagine abelian surfaces. And the generalization of supersingularity is then superspeciality. So we want to look at superspecial abelian surfaces. Those surfaces come in two flavors. Most of the time they are irreducible, which means they are the Jacobian associated to of a hyperelliptic curve of genus 2. And but there's also another type of abelian surface. Those are reducible surfaces that are just a product of two elliptic curves. That's again, if you look at the analogy from before, if you look at a product of two lines, you will get a plane. And so here, if we have a product of two elliptic curves, we get an abelian surface. Okay, and so our first idea in this approach was to now do a random walk in this isogeny graph of superspecial abelian surfaces. And the idea is we just start with a reducible one for some elliptic curve that we know already, that is supersingular, and then we do an isogeny walk with high probability. The first few abelian surfaces will be those irreducible ones that we are not interested in, but at some point we will end up in a reducible abelian surface, which is the product of two elliptic curves, and then one of those could be our new supersingular elliptic curve. So unfortunately, there are two problems with this approach why this can't work. The first one is, it's something that you can already see from the numbers there above. The reducible abelian surfaces are very sparse in the isogeny graph. So one would need to take a lot of steps until we reach such a product of elliptic curves if one just does a random walk, or maybe a number of random walks that are short. And the second problem is even more serious. Assume we would know how to find such an elliptic product very fast, then the isogeny walk still will leak information about the endomorphism ring of the elliptic curves that we get in the end. So one can recover the endomorphism ring again, and that's something that Ross explained is what we want to avoid in our approach. Okay. Okay, then I'll just go over our second idea, also still in the genus 2 setting, very briefly. So there's another idea that geometrically, if one forgets about some information, the principal polarizations of an abelian surface, then it's actually isomorphic to a product of elliptic curves. But it's not clear how to construct this isomorphism. And the main problem here is that abelian surfaces are really complicated objects. So you could think like an elliptic curve is one-dimensional, it lives in two-dimensional space, and is defined by one equation. In contrast to that, one could expect that an abelian surface is two-dimensional and lives maybe in three-dimensional space defined by one equation, but that's not the case, as you can see here. For example, there exists one representation where it's defined in P15, so in a 15-dimensional space defined by 72 equations. So that's really something that we cannot handle very well. But there is a very easy object that's associated to this abelian surface, which one obtains if we just identify every element with its inverse. And so we're working with this so-called Kummer surface. And here there are again some problems with this approach, and that's, for example, that if we have an elliptic curve that lives on the Kummer surface, it might not be an elliptic curve on the abelian surface. But in theory, we know how curves on the Kummer surface have to look like so that they are elliptic curves on the abelian surface again. That said, in theory, we know how they should look like, but in practice, we couldn't find any that have those properties that we wanted. Okay, so now I'll give to Kate for the last approach.
Okay, So it looks like I have like 2 minutes to tell you about quantum computing. One possibility is to look for a quantum algorithm. Maybe I'll skip this slide and say that this approach was inspired by Kane, Sharif, and Silverberg, who are speaking tomorrow in Math Crypt, so I hope you'll come and learn about quantum money from quaternion algebras. The idea is to take a look at the CGL hash function, which was a random walk in the graph, and instead try to do that on a quantum computer. The problem with CGL is that you have a path as you go, so you have always, the output comes with a path information to some curve that you know something about. So here, the idea would be to use a quantum continuous quantum walk. And so instead of using the adjacency matrix of the graph, you take its exponential, which I'm calling u here. That's a unitary operator, which means that a quantum computer can implement it as a gate. And so now we're going to do kind of like you imagine a Markov process in the classical situation. The space is essentially one basis vector for each elliptic curve in the graph. But then a superposition in the quantum computer is some linear combination of those curves. And so you evaluate this, this type of random walk. Okay, so you can get a probability out for what it would look like if you measure where you're choosing t in some continuous interval here. But this is hard to analyze. And so it turns out that if you let that interval kind of grow off to infinity, you get something which is a little bit easier to analyze. So this is from the last slide right there. So the phi j in this expression here are the eigenvectors of t. And so those are something that we know about from the math side of things. And this notation, if you're not familiar with the quantum notation, is basically inner products there. So what's special about the situation with these Brandt matrices is that the eigenvectors are simultaneous for lots of different t's for different l's. So as you look at the L1 isogeny graph, the L2 isogeny graph, and so on, you still have the same eigenvectors. And that allows you to generate an algorithm which will actually sample from this distribution, uses phase estimation. So first thing we would need to know is the distribution uniform? The second thing we would need to know is that the information the algorithm reveals is safe. The phase estimation method will reveal approximations of the eigenvalues. That's just part of what comes out. You have to measure something in the algorithm, and you learn that information. So is that a security leak? This is sort of a question about the structure of the isogeny graph. It's something about the graph theory of this Ramanujan graph. And then finally, this is maybe the fundamental problem, is that this isn't like a hash function. You don't have a seed or something that you could use and some pseudo-randomness. This is quantum randomness. So there's no way to verify that when you get an answer out of this, that it really was a quantum computer that you were using. You can't reproduce the computation. And so, so this sort of fundamental problem gets you right back to where we started, which is you have to have a trusted authority. But there are ways to verify quantum computations. I don't know too much about some of those things, and so this is an interesting open problem, I think. Okay, so this slide is titled Thank You. So we owe a thank you to the Banff International Research Station. This project came out of a workshop called Supersingular Isogeny Graphs with organizers Victoria Decane, Kristen Lauder, Chloe Martindale, and Christophe Petit. And so we owe them a big thank you. That was a really fun conference. It was really fun doing this gigantic collaboration. And thank you very much to CFAIL.
Let's thank all the speakers. I'm not sure if there's time for a quick question.
There's one at the back.
Yeah, I see one hand. Okay.
Sorry.
When you say that the root elliptic curve, do you mean that you recover the G invariant, and from the G invariant you recover the elliptic curve?
When I say what, sorry?
The root. Because you had an approach based on, I think, Hilbert polynomial, where you find the root, and then you say that the root corresponds to elliptic curve. So I had a hard time following that part.
So you're asking about the iteration at the beginning, right?
Yeah.
Does this not let you go?
Is that a quick question?
Yeah, maybe I should answer that offline.
Okay. Let's take that offline. Before I let you guys go, I do want to say that I hope you will all be back at 1 p.m. I'm really excited to let you know that we have Amit Sahai giving a keynote speech here in Corwin East.